Let's get started. So I'm going to post a note about everything that we discussed last week and what we are going to discuss today. Probably today. It's mostly done. So today I wanted to talk about Bellman's equation. So and it's for policy evaluation. So the statement that we are after is as follows. Take a finite MDP as usual. Take a memoryless policy in the finite MDP, which assigns distribution of reactions to each of the states. And consider the value function of this policy. The value function is going to satisfy an equation of the following form. The value of policy pi at state S is going to be the sum over all the actions, the probability that is assigned to the action by the policy times the immediate reward incurred when that action is used in that state, plus gamma times an expected value, in a way, of the value over the next state if action A is used in that the starting state, and we're taking the expected value of the values, future values. And here, recall that R, this value, the immediate reward was just the expected reward that you receive if you are making a transition from state S using action A. And P, this other quantity here, this is the probability of arriving at state S prime, given that you started at state S and you took action A. So this is defined as the sum over all possible rewards. So we are integrating out or summing out the reward component of this transition probabilities, because we are not interested in the probability of seeing a reward together with a state. We are just interested in the probability of seeing a state. Okay, so that's a statement. And the book is telling you some story about why this statement holds. And I said that it will be fun to actually see what it takes to prove this statement. So that's the topic for today. I'm just going to prove this. Okay. So how do we prove something like this? So the statement concerns the value function. So we start. Oops, someone wants to come in. So we start with the definition of the value function. And actually, the last time, okay, we kind of aborted the end of the proof, but we made a statement regarding how the value function looks like, or like an alternate expression for the value function. That will be very useful for us today. So I'm going to use that. So that statement was that the value that you get for starting from S and following pi is this infinite discounted sum of expected immediate rewards. No, t plus 1, just t. So last time we were talking about this infinite sum inside the expectation, outside of the expectation, and swapping out the random reward to the immediate reward. And here the expectation is with respect to the probability distribution that is induced by starting policy from state S. So that's like this little delta S that indicates that we are starting at state S and then following policy pi. Okay. So we start with this. And we're going to separate the first term from the remaining terms. And that's pretty much the same thing as what the book does. But then we are going to argue for the remaining terms slightly differently, but the essence of the argument is the same. So the very first term for t equals 0, so this is an infinite sum. You can break out the first term and then the rest of the terms. The same thing. So the very first term is just the expected value of the immediate reward at time step 0. That's it. Plus, we're going to have an infinite sum maybe, yeah. Okay, so first I write it this way. So we just broke the infinite sum into two parts. And then here you are saying that, okay, like we start with gamma to the power of 1, and then there is gamma to the power of 2, and so on and so forth, so you can pull out a gamma. So let's do that. So you get gamma to the power of t minus 1 here, and you can pull out a gamma over there. All right, so let's deal with the very first term. What's your guess? If we go back to the statement here, what does the very first term correspond to? Is there something that you would think that, okay, maybe they are aligned?
That'd be the R for the reward given the state edge.
Yeah.
So,
Right. So it's like, it's kind of a trick question because you have to break up these parentheses, and then you will have this guy, and then this can also distribute here, and you have this other guy, and this first sum should be intuitively the first expectation over there. So let's see. So let's deal with this expectation first. So how to calculate an expectation like this? There are a few basic things that we can do. So there was the definition of expectation for discrete random variables. You could try to use that. Or if you have some random variables, and then there is a function on that random variables, there is an expectation of that value. There is also some formula for that, right? So there was a formula that said that both are going to work, and both are going to give you the same value. But maybe in this case, it's a little bit quicker to remember that if x was a discrete valued random variable, taking values in a countable set x, then you had a function f, which was mapping from the possible values of x that x can take to the reals, then the expectation of f of x, so x here is this random variable, this expectation is the same thing as the sum over all possible values that this random variable can take times the probability that the random variable is going to pick that value times the value that f takes on that value. That's a corollary of the definitions. It would be an early statement when people introduce expectations, then they prove that this holds from the definition. It's also, if you go back to the book I'm recommending, it's there in the first chapters. Okay, so let's use this to calculate this. So what is our x? Do you have a question?
I have a question and an inversion. What is the symbol right after like the first of the two between I? It looks like a DS or a
This one?
On the main cover.
Here. This data is?
Yeah, what's up?
Yeah, so that was this distribution that puts a unit mass on state S. So this is this function, this probability mass function, such that it's over the states. So for any state S prime, by the way, there is no embarrassing question. It's okay. So for any state S prime, the value that this function takes is just 1 if S prime happens to be S, point mass there, and 0 otherwise. So that just signifies that, okay, so that was the initial state distribution. This distribution is very special. It's such that it puts a point mass on state S. So that just says you're starting at state S for sure, with probability 1. It's called the Dirac function. It's for the discrete case, and people define it for other cases as well. But for us, the discrete case is good enough. Okay. Yes, please. If I write something on a board, it's not legible, you can't see it, or maybe you just forgot the definition, it's okay to ask because you might not be alone. Other people may have the same question. If it is becoming too much, then I will stop you. So don't worry about that. We should discuss these things. All right. Anyway, so back to here. So this expectation is respect to a probability measure or probability distribution, right? So we have a probability distribution, and there is a corresponding expectation. It's indexed because this probability measure and the corresponding expectation depends in a particular way on this initial distribution and the policy. We had these definitions, right? Like we were setting up how this probability distribution looks like, how it's connected to what's the probability of, seeing a particular history That's all connected to the initial distribution, the transition kernel of the MDP, which is there on the board, and the probability is assigned to the actions by the policy. And here we're just using that. OK, so let's go back to calculating this expectation. We want to use that little statement over there. We have to add, we know what P is. P is the underlying measure. This is this P delta S pi. That's the probability measure. We need to have a random variable, x. What is our x? And we need to have a function f. What is our function f? How do we use that result?
The x is your tuple basically of s naught a naught, and your function is r of that.
Right. So if I want to use that result, I can set x to be this pair. So S naught and A naught, they have a random variable. You form a pair of them. It's another random variable. And OK, that's x. And then the function f is going to be what? So what are the possible values x can take? So this funky x, calligraphic x, is going to be just like all possible states, the combination of all possible states and actions, because S naught takes in values in this set, and A naught takes values in this set. You take all possible combinations. There's no other value that X can take. So what is F now? F is going to be just R, which is a map from these pairs to reals. OK. So we set up this thing. So we just have to use that statement. And OK, continuing here. So this thing here is equal to the sum over all possible x's. So that's like state action pairs. SA in S cross A. The probability that x takes on value SA, but instead of writing x, I immediately write S naught and A naught. OK? So probability that S naught, A naught as a pair takes on the value of SA. And this probability corresponds to these expectations. So in the index, we have delta S and pi. OK, times the value f takes at x. So that's just what value the reward takes. What's the immediate reward function gives you at the pair SA. OK. All right, so to get a final value, all we have to do, all that is left to do, is to deal with this probability. The other guy, we already see it here. So what is this probability? So first of all, the condition that this pair takes on the value of little s and little a is the same thing as saying that S naught takes on a value of S and A naught takes on a value of A. All right? So that's just a different way of writing the same event. So their probabilities are the same. And here, we can use conditional probabilities, let's say. So this is the same as the probability of seeing that A naught is equal to A, given that S naught is equal to S, times the probability that S naught is equal to S. Just a definition of conditional probabilities. Okay, so maybe maybe this was superfluous, but maybe not. You can do this in so many different ways. This is just one way. And then there are two questions. What is this probability and what is this probability?
The second one's just one, right?
It's, whoa, okay, so we have a symbol clash here. So that should be, maybe I index this with A naught here, or S naught A naught. I think that we just ran into some trouble because we recycled the letter S for two purposes. It was used for summing here, and it was also used in the initial distribution, so don't do that. All right, so know that I fixed that. And go back to this question. Okay, so what is this? So we start from the initial distribution, delta S. What is the probability that we are finding ourselves at S naught, at time step 0? One? When? So let's say you have two states. S is state 1, and S naught could be state 1 or state 2. Huh? Yeah, you could write that this is delta S at S naught. So you're right, it could be 1. It is 1 when S naught is equal to S. That's what you were thinking about, right? But otherwise it's 0. So it's just like, if you want to write it compactly, then you can write S. Okay. So what about this other probability? Pi at, yeah. Tell me what to write. Pi? Yeah, okay. That's right. So regarding this probability distribution, this one. So the last time, unfortunately, we don't have some way of pulling what was on the board the last time. But I said that this probability distribution satisfies 3 important properties. And any probability distribution that satisfies those 3 important properties is one that we can work with. So they are kind of uniquely identifying these probability distributions. And one of the important properties was that the initial distribution, according to this probability distribution, is what is prescribed here in the index. That was property 1. Property 2 was that the probability of seeing some action happening, given the history, in this case, the history is just one state, is exactly what the policy is going to describe as the probability. So we're using that property here. We haven't used the third property, which would be that the probability of seeing a next reward in the next state, given some history, is equal to the probability that you see here, right? We'll use that too. Anyway, so we have this. So we can continue writing our expression. So this is continuing here. This is equal to the sum over S naught and A naught of delta S, S naught, pi A naught given S naught times R S naught A naught. Okay. So this sum, it's a double sum. So that means that you can sum over first the A's and then S's, or the other way around. So we could write it by first summing over, I don't know, doesn't matter. Let's move the states inside because that will be more convenient for me. All right. So when we are summing over all possible states S naught, these values, what do we get? There are two possibilities. Either S naught is equal to S, and then we got a 1 here, and then these other guys multiplying it. So just these two other guys, but then S naught is equal to S. Or S naught is not equal to S, and then we get a big fat 0 there. And when we get the 0 there, then it doesn't matter what we have over there. So all the terms in this sum are either 0 or this very specific value. And that just happens when S naught is equal to S. So this inside sum, it's just pi A naught given S times R S A naught. Okay, so that's the inside sum. And then you have the outside sum, which is over the actions. I will just keep that. Good? And if you look here, this is indeed these two terms. So I can put a check mark here. This is checked out. We still have to count for this multiplied with this and sum over the actions. So that part isn't accounted yet and accounted for yet. Okay? All right. So let's move on to that part. I'm going to erase this. Clear? Right? No questions for that. That was relatively easy. I mean, once you know that, you have to use that. Just a few steps. It's just a lot of writing. So once you practice this enough, you can do all of these things in your head. You don't have to write, but I think that it's good at the beginning to write a little bit more so that we get used to the idea of how to do these things for real before we jump to the conclusion that, oh yeah, like this is how it should be done. Because remember, the square and the circle, things sometimes are not what they look. All right. Okay, so let's calculate the other term. So we actually do have this helpful gamma over there, so we don't have to worry about that. It's also there. Here we have this infinite sum, and inside the infinite sum there are these expectations. So let's focus on those expectations. Then see what happens. So let t be greater than or equal to 1. And let's do a calculation on this. Well, once you learn a hammer, you got to use it. So we can write this as the sum over all possible values of states and actions times probabilities of seeing those states and actions at time step t under the given probability distribution. So using the same result as before, I think that this is called the law of expectations for naive statisticians or something like that. Never remember this. The statisticians. Because it's like so logical that it should be like that. Okay. Not naive, unconscious. All right. So let's use the law of expectations of unconscious statisticians. Oh my gosh, that was a mouthful. So some were these states of the probabilities all right. That was easy enough. So now we have to deal with this. And here is a funny thing. Okay. I put in this T here. So let's keep it. So here, it's not entirely automatic what you need to do, but if you read the book, you kind of know that you just want to argue that if you make a step after in the MDP, so you take an action and you see a next state, and when you're at the next state, things look the same as before, condition that you arrived at that next state. That means that the future, the distribution of the rewards, the sequences of state action pairs, everything is kind of the same as if you started in that state. So that's kind of the Markov property, right? So the idea is that you don't have to know what happened in the past. If you're conditioning on that you're in a state, the future from that state looks like the same as the future looked before. Here it's important that we are using a memoryless policy. If the policy itself had some memory, then that would not be the case. But if the policy is memoryless, this will be the case. And we have a memoryless policy. So at this step, we're going to use that. So we want to use this idea. So we want to write this as with the help of conditioning that you arrive at some state. So here, T is greater than or equal to 1. And we don't know what state we are going to arrive at. So we have to sum over all possible states that we could arrive. Take the probability of those states. And then take the probability that from that state on, we're going to end up at this particular state action pair. Right? Okay. So we just expanded the probability using conditional expectations. So nothing much really happened there. So let's calculate the various terms here. So what is this term? It's a marginal probability of saying that you're at state S1. I think I should condition on, okay. I also put in the state, the action that we are using at time step 0. It's going to be less work. Right. So now if you do what we were doing before, it's just one more step, because previously I think we were calculating what's the probability of staying, I don't know, some initial state, some action together. So now we don't have the initial state, but we actually know that the initial state is going to be S, is probability 1. So you can use the law of total probabilities to, you want to be totally formal, then you introduce this additional, even that S0 is equal to S0, sum over all possible values of S0, and write out all these probabilities. Okay, let me just do it rather than. And then you can just write this as the probability that initially you're at S0, and that's all very familiar. We know that that's just the Dirac S at S0. So this sum is actually going to go away times the probability that A0 is equal to A0 and S0 is equal to S0 times the probability that S1 is equal to S1 and S0 is equal to S0 and A0 is equal to A0, right? And all these probabilities are indexed by delta S and pi. Okay, so this we have seen before. This we have also seen before. This is the probability under policy pi of seeing A0 being used at state S0. This is the third thing that I was alluding to before, which is the probability of seeing the state S1, given that you started at state S0 and you use action A0. And that probability is just that little probability over there. So that's PS prime given, PS1 given S0. All right. Okay, so that's, if you do the sum, everything goes away because you get a zeros everywhere except at state S. So you effectively have just to think that this is S, and you have the A0. So this whole thing is pi A0 at S times P S1 given S0 A0. So that's this. It's not very surprising if you're thinking about it, because this says that you start at state S. You're going to use policy pi. So what's the probability of seeing all this? Well, you first have to choose an action. Probability of choosing that action is exactly this. And then you have to see this state. And the probability of seeing that state, given that previously you have been at S, because that's where you started, and you used action A0, is exactly what's given by this little p function. So that's probability of S1 given S0 and A0 according to this guy here. Okay. All right, so we are done with that. So that remains to calculate this guy. Maybe I do that here. Is this clear? Yeah. Okay. Well, what are we conditioning on? A0. And S1 being S1. All right, so this conditional probability is only well defined if the conditioning event has a positive probability, but we don't have to care about the events which do not have a positive probability, because then this guy would be a 0, so we don't care about this definition, so everything adds up. So the conditional probability, we will only need to calculate it when this is positive. Okay, so let's calculate it in that case. So let's assume that A0 and S1 are such that this probability of seeing A0, the first action being this little A0 and the first state being little S1 is positive. So in this case, so this is the assumption that we use. This is just this probability. Okay. So when you are using LaTeX, you would copy paste, and it's a little bit faster. So just taking the intersection of all the events and then divide by this probability here. So this probability comes here. That's why we were taking the precaution that that shouldn't be 0, because otherwise we would be dividing by 0. Not clear? Clear? Okay. So now we're going to want to use, actually, what am I doing here? Yeah, okay. So now we are going to claim that this is nothing but wait a minute. Yeah, okay. This is the same thing as you start at state S1. So here, I changed this index S to S1. And I'm shifting the indices. So ST minus 1 is equal to ST. T minus 1 is equal to AT. And there is nothing else. All right. That's a claim. How do we prove this? We have this probability. We have to write it out. What is this probability? We can use the law of total probability. And we can use the law of total probability to write this out as well. And we're going to match terms. And hopefully things are going to work out. 4 minutes to do it. All right, so the probability in the numerator is this. And that seems difficult to handle, but if I introduce a big sum, where I will have all the other terms, all the other states and actions and everything, then it will be easier. So I start with A naught equal to A naught, and after that comes the first state. So I just copy this in the reverse order. After that comes, I don't know, A1 equals to A1, dot, dot, dot. Actually, let's write S2 equals to S2. And then ST equals to ST and AT equals to 80. And I need to sum over everything, all the lowercase letters that don't appear here. So that's the law of total probability. That's what it gives me. So what do I sum over? A1. And then S2. And then dot, dot, dot. And AT minus 1. And ST minus 1. OK? All of these. Oh, this is not really working, this black. OK, so we know this probability is. So that was the definition, basically. So that's the probability that A naught is taken by policy at state S, because we are starting at state S. Then the probability that we make a transition to state 1, given that we were at state S0 and took A naught, and then the probability that we take action A1 in state 1 up to here, the end. All right. And now let's focus on this term here. So you can do the same thing. You can just sum over everything from the beginning. But we are starting at state 1, and yeah. Let's just use the same indices. So this is so we have to sum over everything which doesn't appear here. So that's all A1 to, I don't know, AT minus 1 and S2 to ST minus 1. And you can write this out as well. And you write it out, and you will find it's the same. OK. So after, OK, it's not the same because here, this probability is going to be divided by this probability here. This probability is P I A naught given S times the probability of S1 given S naught and A naught. So once you do that division, OK, these two guys go away. And this guy is what's here. OK, after doing all this. I managed to run out of time again. Right, so let's, I will post in the notes. It's there. I have to learn to manage time a little bit better. These proofs are too long. We're very close. So dissatisfactory. It's this close.